This is the section 7.1 part 1 notes, the inverse sine, cosine, and tangent. Now, as I said on Zoom, these are going to be kind of some lengthy notes, but that's okay. We're going to be able to work through this without any major issue. So we're going to start thinking about inverse functions. So I'm going to think about the inverse sine function to begin with. So we're thinking about a function f of x and its inverse function f negative 1 of x, or the inverse of x. So if you recall, we learned that in a normal function, you have an input and then you get an output. Your inverse function is basically saying, I want to work backwards. So in a normal function, you put in an x and then it spits out a y. You put in your independent variable and it gives you a dependent variable. Well, in my inverse function, I put my dependent variable in backwards and it gives me the original independent variable. So it's my way of kind of working forwards and backwards with a function. I'm saying this function, when I put in 2, it gives me 3. So the inverse function, when I put in 3, it gives me 2. It works backwards from where I started. Now, you might recall that we started learning about one-to-one functions when we were learning about inverse functions. And with those one-to-one functions, an inverse function a regular function has to be a one-to-one function in order for it to have an inverse function. And if it's not a one-to-one function, it doesn't have an inverse function. And this is because we learned that those functions are, an inverse function is symmetric to the line y equals x to the original function. So if I start flipping it around and it's not a one-to-one function, it's going to fail the vertical line test. And we can see this example here for f of x is equal to the sine of x. We can see that the sine function is not a one-to-one function because it's failing the horizontal line test. It's going through that function many, many times. Therefore, there's no such thing as an inverse sine function as a base level. And you're going to see our workaround for this because we do have a workaround for it. And the issue is here because you can see we've got this periodic function. It's repeating its y values over and over. If I were to go through and graph this function reflected over this line, it would look like this. So that means it's failing the vertical line test. I can't draw a vertical line through this function, so that's not working for me. I can't just say the sine function. And I've got more on why this doesn't work here. So if I asked you for the inverse sine of 1/2, and what this is asking me here is what theta is sine of theta equal to 1/2. That's what this inverse sine function means. So I go ahead and I start asking myself, all right, what angles theta give me this? Well, I know pi over 6 is going to be one of them. And I'm going to write this off to the side. That's because the sine of pi over 6 is equal to 1/2. Well, wait a second. The sine of 5 pi over 6 is also equal to 1/2. So that means that theoretically I could also write 5 pi over 6 here. And I could continue this. I could start thinking about more and more of these thetas. So I'm going to think about the fact that 13 pi over 6 would fit this bill, as well as 17 pi over 6, as well as 25 pi over 6, so on and so forth. So if I asked you what is the angle that fits this, there's so many angles here. And I can't just go through and type out all these angles over and over and over. It would take me forever. And honestly, you would be going for infinity because it would every single angle. This is cyclical, so it goes on forever and ever. So I can't just say it this way. I have so many different values it could be. But I can restrict the domain of my sine function. Now I can consider the fact that my sine function doesn't repeat itself between negative pi over 2 and pi over 2. And now what I've done is I've created a function of sine that is a one-to-one function. I put these endpoints here, so you can see these endpoints that I've added in. And what those endpoints do is it allows me to consider this as a one-to-one function. We can clearly see that it's passing the horizontal line test at this point. So now when I create the inverse function, I actually can say, all right, the inverse function here, when I reflect it over this line, y equals x, is going to look something like this. It's going to look something like this when I reflect it. So sorry about that. It's going to look something like that, and we'll change colors here. I'll go through. It's going to reflect over this line, y equals x, and then it's going to come up this way. And that's not a perfect drawing. That's just kind of a slight squiggle to show you what this is going to look like. But now I have that line, y equals x. I know it's going to reflect over that line, y equals x. And so that's what my inverse sine is going to look like. And now that inverse sine, even though I've drawn it to almost look like a vertical line pretty poorly, I now know that my inverse sine will pass the vertical line test because I've got it restricted there. Now I do have a brief note here. There's an infinite number of ways that I could restrict the graph of sine as long as I only looked at it over an interval of pi. Again, I could restrict this from I could restrict this from 0 to I could restrict this from pi over 2 to 3 pi over 2. I could restrict this from 3 pi over 2 to 5 pi over 2, so on and so forth. I could restrict this so many ways that would allow me to look at my sine function solely as a one-to-one function, which would allow my inverse function to exist. But mathematicians have agreed to set it from negative pi over 2 to pi over 2 for any unspecified function. Now I theoretically could say, let's think about this sine inverse function, and let's think about it for these values of theta, and in that case it would be specified, but in all my time teaching math, I've never ever seen that specified that way. That's purely a theoretical thing at this point. So what this means is that if I'm finding the inverse sine function, when I say y is equal to the sine inverse of x, that's meaning I'm saying x is equal to the sine of y. So again, if I'm saying y is equal to the sine inverse, and this would better be reported as opposed to y, theta is equal to the sine inverse of x, that means that my x value is equal to my sine of theta. I'm trying to figure out what angle, when I take the sine of this angle, what angle is it that gives me that x value? So whatever I have inside of the sine, I'm asking, what is it? This is a value that I know. What is the angle that makes this happen? Now, this x value has to be between -1 and 1. If this x value is greater than 1, it just simply doesn't exist because the domain or the range of the sine function. The range of the sine function is between -1 and 1. So there is no angle that has a sine greater than 1. If you are being asked what angle is it that has a sine of 2, there is no angle that has a sine of 2. Just like that y value, and we've already stated that those thetas have to be between negative pi over 2 and pi over 2. We're restricting its look so that way we know the exact angle we have to report. So let's look at it. And these are the unit circle. So these are the common ones that you're going to see. These are the ones that appear in the unit circle all the time. These are our known values. If you see the inverse sine of -1, you know your answer has to be negative pi over 2. If you see the inverse sine of 0, you know your answer has to be 0. If you see the inverse sine of root 3 over 2, you know your answer has to be pi over 3. Those are just the unit circle angles that already exist in that range. So if I want to look at some inverse sine values, the inverse sine of 1, I'm going up here and I'm looking, okay, what sine theta has a sine of 1? Oh, pi over 2 gives me a sine of 1. So if I'm taking the inverse sine of 1, my answer here is pi over 2. And this is because the sine, the regular sine of pi over 2, is equal to 1. Okay, what's the sine inverse of -1/2? I go up here, I look, and I see, oh, there's -1/2. -1/2 corresponds to negative pi over 6. So that means that negative pi over 6 is my answer. And again, this is because the sine of negative pi over 6 is -1/2. And there we have it. So that's why I have those answers. I'm just going through and saying, what is this angle theta that makes this the value of sine? Now, the next thing that we'll have to know, there are some values that you can just plug into your calculator. You don't have to worry here. If you're in degree or radian mode, you can report your answer in degrees or radians depending on what mode your calculator's in. It might be specified, but I don't really think that I would. I'll post a video on Google Classroom so that way you're aware of how to do this, but this is pretty clear. So if you look at your sine, cosine, and tangent button on your TI graphing, you'll see that second color you're going to see an inverse sine, an inverse cosine, and inverse tangent. So what I would do is I would hit second, and then I'm going to hit the sine button, and that's going to give me my inverse sine. Then I'm just going to type in 1/3 into the parentheses, end them, and then hit enter. And then it's going to give you an answer depending on what mode you're in. My calculator is currently in degree mode, so I have 19.47 degrees. I could also go ahead and move this to radian mode just for fun. I'll put this in radian mode, and then I'll do that exact same thing. So I will hit my second button. I will hit sine to get the sine inverse, and I'll type in 1/3. And then I'll find that this is the same thing as 0.340 radians. So either of these could be correct depending on what mode you're in. It could be specified, could be unspecified. I'll do the sine inverse of 1/4. Again, you just hit second, you hit your sine button to get your sine inverse. I'm going to type in 1/4. I'm going to find that this is equivalent to 0.253 radians. I'm also going to go ahead and I'm going to move my mode to degree mode here. I'll hit second, I'll hit the sine button, I'll do 1/4, and I will find that this is equivalent to 14.48 degrees. And there you have it. Those are both correct answers here. I'm just plugging into my graphing calculator and paying attention to which mode my graphing calculator was in from the beginning. Nothing too complicated. Now, this is where it starts getting weird. We've learned this prior. So if you recall, if you plug a function into its inverse, if you make the composition function of the inverse of the function, it's going to be equal to x, just like if I plug my inverse function into the original function and make this a composition function, it's going to be equal to x. It's whatever is equal there. So I have some rules here of the inverse sine of the sine of x is just equal to x. But it's only for these angles. And this is going to get a little bit complicated. But I trust that we'll be able to figure this out, especially when you see the video answer key. And you'll be able to ask me some questions on this later this week. As well as if I take the function of the inverse function, so the sine of the sine inverse of x is just equal to x, as long as -1 is less than x, which is less than 1. So let's go ahead and practice this. I look here, and I have the inverse sine of the sine of pi over 8. And if I look up here at my rule, my inverse sine of the sine of x is just equal to x as long as that x is in between -pi/2 and pi over 2. Well, pi over 8 is in between these values, so my answer is just pi over 8. It's going to repeat itself here. That's it. And that's my answer. I see that pi over 8 is in fact between -pi/2 and pi over 2, so I'm satisfied with that. I'm really happy with that. Just like for b, I'm going to look at b. I'm asking for the sine of the sine inverse of 0.5. 0.5 exists right here between that -1 and 1 because I'm talking about something where my sine inverse is on the inside. So I come down here and I say, all right, that means my answer is 0.5. It's as simple as that. Let's jump to D before I do C because D is the same case here. I hope we can all see that 0.8 does exist between -1 and 1. My sine inverse is on the inside, so that means I'm looking for values between -1 and 1. So my answer here is just 0.8. Example C is where it gets a little bit complicated. I'm looking for the sine inverse of the sine of 5 pi over 8. Well, what we can see, 5 pi over 8, I have to have my x, because my sine's on the inside, is between -pi/2 and pi over 2. 5 pi over 8 is greater than pi over 2. So what I'm going to do is I'm actually going to draw 5 pi over 8. This is the angle 5 pi over 8. It ends in quadrant 2. We should be able to see this because it's less than pi, but it's greater than pi over 2. Now what I say to myself is, oh, this is 3 pi over 8 from the x-axis. And it's occurring in quadrant 2. In quadrant 2. In quadrant 2, sine is positive. So since sine is positive, that means that it's going to have the exact same sine value as an angle that is 3 pi over 8 here. So these have the exact same sine value because their y values are going to be the exact same y value. And now that I know that, my answer here is actually going to be 3 pi over 8 because it's 3 pi over 8 away from that x-axis in the positive quadrant. And that is how I figured that out. That is not the easiest thing to wrap your head around, but I'm thinking about how far away it is from the x-axis and how to make that match quadrant 1. And I'm going to make sure you have an example of this on your video answer key as well. And again, I anticipate a couple questions on this, and I'm going to do my best to explain it. But you have to consider how far your angle is from the x-axis. All right. Inverse cosine. So it's just like the sine function. We're going to restrict our cosine function. So with our sine function where we restricted it from negative pi over 2 to pi over 2, we don't do that with cosine. Cosine we restrict from 0 to pi. If we think about our line y over x, we're going to create something that as we would reflect it over the line y equals x, we've got something happening here. So it's going to do something kind of like that. Let me actually pull this up. I hate thinking about these things. Okay, here we go. It's actually going to do something like this, where it's going to start down here and then go up like this. So it's going to end up reflecting over the y equals x line like that. So now we can make it, it's going to pass the vertical line test. Again, just a rough sketch, but that's how it would end up reflecting. So now we have our inverse cosine function that way. These are the cosine within the unit circle. So we should know these angles of, if I'm being asked what is the inverse cosine of 1, it's always going to be 0. If I'm being asked what is the inverse cosine of 0, it's always going to be pi over 2. These are the unit circle angles which we can work with. It makes our life easy. So here, what is the inverse cosine of 0? I go up to this chart. I see that what is the theta that gives me a cosine of 0? The theta that gives me a cosine of 0 is pi over 2. So that's my answer. What is my cosine that gives me, what angle is it that I have a cosine that's negative root 2 over 2? Well, that is going to be 3 pi over 4. And I say, all right, cool. That is my angle, which gives me that cosine value. And that's all I need to know, especially the unit circle angles. These are pretty straightforward. And we have those same rules for the cosine inverse of the cosine of x is equal to x as long as x is between 0 and pi. And then the cosine of the cosine inverse of x is equal to x, where negative 1 is less than x, which is less than 1. So it's going to fall in between these values. So let's go ahead and look at that. We've got our cosine. So we've got the cosine of the cosine inverse of pi over 2. We're doing the, this is the cosine inverse. So we have to consider this. We have to think about, is pi over 2 between negative 1 and 1? I've kind of done like a little bit of a trick here. This is not an actual radian. Pi over 2, well, this is equal to 3.14 over 2, which we're going to see This is less than 1. So this means that my answer here is just going to be pi over 2, because 3.14 divided by 2 is in fact less than 1. What is my cosine of the cosine inverse of negative 0.4? That falls between negative 1 and 1, so my answer here is negative 0.4. What is the cosine of my cosine inverse of pi? So here I'm talking about the cosine inverse yet again. I've tricked you by giving you this radian value. Pi is greater than or equal to 1. So this just doesn't exist. There is no such thing as an angle with a cosine equal to pi. It's way, way, way too large of a value. Cosine values exist. The range of cosine values exists between negative 1 and 1, so that does not exist. And then for D, I'm taking the inverse cosine of the cosine of 2 pi over 3. 2 pi over 3 does fall. It is greater than or equal to 0, and it is less than or equal to pi. So that means my answer here is just going to be 2 pi over 3. Now, inverse tangent, I'll just quickly show you the graph of tangent. Tangent's a little bit more straightforward in the fact that as I draw my coordinate plane, we can quickly see, well, we've got our asymptotes that exist for tangent, and then tangent is like this. Oh, well, that's really, really nice, because as we transform it over this line, y equals x, well, then we just get a function that looks like this. And it's going to kind of keep going on and on and on forever like that. And what we have here is we have an ongoing function forever and ever, but it's going to exist like this. So these are going to become horizontal asymptotes. So what we're going to consider for this is our theta, or our x value, also is going to be restricted to be greater than or equal to negative pi over 2, but then less than or equal to pi over 2. So when I'm trying to figure out what is this tangent of negative 1/3, I'm just asking myself, okay, what angle in the unit circle gives me a tangent of negative 1/3 that falls between negative pi over 2 and pi over 2? Well, that is negative pi over 3, so that's my answer here. And then what is my inverse tangent of 0? That's 0. We already know that. The tangent of 0 is 0. And then we have these same rules for the tangent function. You can see here that the tangent inverse of the tangent of x works where x is between negative pi over 2 and pi over 2. Now the nice thing about the tangent of the tangent inverse of x, it works for any value of x. As long as x falls between negative infinity and infinity, it works out for you. So that's good there. Any value works. We don't have to worry about any restrictions. We don't have to worry about things that do exist or do not exist. So that's really, really nice. I'm not going to have any examples of that. I'll make sure I have an example on the video answer key for you guys, but that should be about it. Your homework is textbook page 438 between numbers 13 to 52 all. So textbook page 438, 13 to 52 all. I'll make sure to do a couple examples for you guys on the video answer key, the regular answer key as well. Again, reach out with any questions. Email me earlier rather than later. Thank you and have a